So this talk, bird's eye view, is going to be kind of a primer on quantum software. There's a lot to unpack, and 25 minutes isn't a whole lot of time, so we're going to do the best we can. So hopefully it's not too high level. If anyone wants more information, more details, I'm happy to give recommendations for reading and papers. But for this, we're going to kind of start with a high-level overview, a little bit of a history and the current state of things when it comes to quantum software before really turning our focus on compilation, what the compilation pipeline looks like, kind of in a very simplistic form, before we go into future directions and research areas for these spaces. And like I said previously, we're going to highlight areas where I really think that there's great synergy between computer scientists focused on quantum software and applied mathematicians. So let's go ahead and get started. So first, we'll begin with why quantum software. And just in general, I want to highlight that software is a tool that we use. Beginning with Fortran in the 1950s, you saw kind of a transformation in the way that we were able to implement scientific computation, and that was hugely enabling for research in general. So why quantum software? Simply because, kind of from both ends of the spectrum, it'll help us to make progress in quantum systems. We want to have wider adoption of quantum technologies, and that's going to require us to have ways to specify quantum algorithms in a way that's a bit more streamlined, a bit more consistent, and then ways to take those representations, those abstractions, and target them toward hardware. So quantum software helps with both ends of the spectrums. It provides us with languages that allow us to reason and verify our logic. It allows us to transform and optimize those high-level specifications into low-level representations, which is what we're really going to highlight today, so that we can run them on hardware. And then it enables us to not only create these software pipelines that kind of get ideas to hardware, it also creates this kind of parallel set of tools that allow us to improve our understanding of quantum systems. So for example, QTIP is a tool that we use to model open quantum systems, and since all quantum computers are open quantum systems, we need to have a good understanding of how they work. So there's all these kind of parallel adjacent software tools that help us create this software pipeline to target hardware. And finally, just really emphasizing that quantum software accelerates research. With software, we're able to have results, algorithms, and workflows that are made public, especially with open sourcing, which is huge. It kind of leads to software-driven research, because once we kind of push the frontier on our knowledge in terms of algorithms, in terms of hardware, we're able to ask new questions and lead to new innovation. So it's quite exciting. So the development of quantum programming tool chains kind of is relatively recent in terms of how much progress we've made in about 15 years. So we first saw the initial programming languages emerge from academia in about 2000. Into the mid-2010s, we saw kind of these early forms of programming languages, first starting with QCL. That was huge. It enabled us to specify a quantum register, so we had a new way to reason about quantum information. And we were also able to reason about it in a way where we could combine that with our traditional data structures and traditional data types, including ints, booleans, strings, vectors, etc. And then we had, one step further taken with Quipper, which is a functional programming language. So we had a lot more functionality, a lot more scalability with Quipper before we got to SCAF-CC or Scaffold, which enabled us to start targeting hardware. So this is kind of the early progression. But then we start seeing in the mid-2010s, late 2010s, all these great companies coming out with hardware platforms. So they needed a way to get people to those platforms. So we started to see software emerging from industry. So we had Qiskit, PyQuil, Cirq, and Penny Lane as just some examples. And that leads us to today. So today, we've got a lot of different packages that are merging, and you can even get a job as a quantum software engineer, which is wild because this field just kind of took off in the last 15 years. And here's just kind of, maybe your favorite quantum software isn't here, but we've got a lot of different packages that kind of emerged. Previously, we really saw a a preference for Python, but now we're seeing Julia, Rust, C++ implementations, and that's helping with scalability. So these quantum software tools, they're really targeted, they're really specialized in many cases to kind of focus on one point in the compute stack, which has been really helpful. But in general, like, this is great progress, but we still need to have more of the quantum software stack filled out. In general, we've kind of seen the fact that we've gotten, we've made a lot of progress in terms of algorithms, we made a lot of progress in terms of hardware, but we kind of need to meet in the middle and build out this middleware. So that brings us to where we are today, and it's a work in progress. So this is kind of one of the areas that really excites me and where a lot of my research lies, is building out the quantum software stack. So we can kind of equate where we are today to where we are in about the 1950s with classical computing. So we had our algorithms, a lot of development there, a lot of development in physical hardware. But how we got our ideas to hardware was a little bit of an open-ended question. So we had this first wave of quantum programming, this tool chain that's developed, but now it's really time for us to focus on building out the software stack in the middle. So coming up with abstractions that allow us to better reason about our programs so we can better optimize them, and then also thinking about ways that we can have efficient ways to interact with our classical compute, because at the end of the day, when we think about quantum computation, it's really a hybrid process that includes not only quantum subroutines, but classical subroutines as well. And then, of course, we have to think about all of the error mitigation, error correction, error management in general, that needs to fold into that as well. So it's a lot of processing, a lot of moving parts. So there's, in general, just a need for architecture to think about how we can coordinate all of these things together. So in terms of software stack research, these are kind of open areas that are very exciting. So device compilation, we're going to dive into that in kind of the next part of this talk. But logic and gate synthesis, numerical methods are often required to do a gate synthesis where we take a unitary, a function we want to implement with our quantum computers, and we need to find a way to decompose it into, factor it into simpler components so that we can transform those into machine executable forms. Programming languages, that's very necessary, especially programming languages that can model the interplay between quantum information and classical information. Resource estimation, error mitigation, optimal control. So all these different things that are really required to build out that center layer of the quantum computation stack. And of course, thinking more further into the future, whenever we have these amazing utility scale systems, we'll need to think about architecture and security for the quantum cloud. If I'm talking to a quantum computer that I'm paying top dollar to run my processes on, how do I know I'm talking to the right machine? And I'm actually talking to a quantum computer, not just a random number generator. And then also thinking about how we orchestrate data movement and processing within a hybrid HPC environment. So once again, that was kind of the bits that fill out the software stack, but there's also these software stack adjacent quantum software tools. So that includes circuit simulators. We have all, that's one thing that maybe I probably should have put a little bit of emphasis on. So, if we could simulate quantum computation, why would we need a quantum computer? So quantum circuit simulation is incredibly hard. Quantum system simulation is incredibly hard. So figuring out better ways that we can implement simulation so we can, one, better understand our algorithms, and two, use simulation and noise models within simulation to help guide us in exploration of improved hardware. So it's a very important space. Design and analysis tools that guide us towards more feasible architectures that help us to scale. Characterization routines, so we can very much triage those errors through tomography, through randomized benchmarking, et cetera, so we can really understand the dynamics of our open quantum systems that we're trying to program. And then finally, benchmarking suites. We can think about, starting with like the spec benchmarking suite, going to the future. We have a benchmark for almost every type of application these days. We really need to think about how we can build out those suites so we can really understand in a more holistic applications level manner how our quantum systems are performing, especially when we're kind of connecting them to classical compute. So these are all different areas that are open for many research questions and open for many areas for us to all collaborate together. So now we'll go ahead and dive into the details associated with the quantum compiler. So first, I want to emphasize that today's quantum hardware is a little bit unreliable. We're working with these prototype systems, and it's pretty across the map. So this is a nice figure from this report that came out earlier this year from a bunch of people working on quantum software and quantum computer architecture that highlights just different types of qubits we have that are kind of at play right now. The current state of things is we don't know what the best physical qubit is going to be. We might not have even invented it yet. But right now we're working with a variety of different systems that are very different. We are seeing devices that emerge that have 1,000 qubits on chip, physical qubits. But unfortunately, many more are needed for fault tolerance. So there's a long way that we need to go to scale. So going back to the differences between these devices, each one of these platforms has different characteristics in terms of architectural constraints, such as different error rates, different coherence times. That affects how long your compute cycle is for that single run of that circuit that needs to be done many times so you can create a distribution so that you can process it. So all these things play into our resource estimations, trying to figure out what is the best back end for a particular application. And there's a lot of variation. It makes it a really challenging problem for compilation of mapping and pairing an application to a back end. And then, of course, too, just the constraint of a lot of these architectures require these very special environments, dilution refrigerators to keep them highly isolated from external noise. So just another thing that adds to the complexity. So not only do you need to program these systems, you need to program them efficiently because there might be restricted I/O going into the fridge to program and make these devices compute. So more about quantum hardware today. Even if you have two chips of the very same technology, they might be very different in the way that their heartbeat it can be picked up on. So we can see these two devices. This is a sample from the IBM Quantum Cloud, so two of their 127 qubit devices that are currently deployed. And we can see that their error profile is very different. It's hard to see here, but what we're looking at is T2 coherence time, so essentially how long a qubit can hold state information. And then we're also looking at echoed cross resonance, so that's the basis gate set that is used by the fixed frequency transmon. We can see that it's a heat map that correlates to the values of those particular errors or coherence times. So we can see they're both very different. So that also adds another layer of complexity to the compilation problem. What works well for one machine, even if it has the same layout, same architecture, might not work as well in another because you might be targeting a part of the chip that's not as robust. So last thing I wanted to emphasize about today's quantum hardware is that in general, we have these systems that are modest in size. Theoretically, you could put a logical qubit or two on them. However, noise prevents us from really scaling up into these useful, exciting circuit sizes. So we aren't able to use all of these qubits together in most cases for collective computation over large time scales. So there's a lot we need to do to scale up the number of qubits and also improve the quality. However, all hope should not be lost. The role of the compiler is to make the most of the hardware we have today. While we do need larger systems, while we do need higher quality systems, there's a lot we can do with software to kind of push the frontier of what exists today. So the role of the compiler is essentially what we want to do with it is to transform a piece of source code, oftentimes it's one that's human understandable, into a machine-ready specification that in such a way that we preserve that program semantics. So what the logic we expect to see, we want to actually implement that in hardware in the way that the hardware understands. So there's important considerations. Just as we talked about, each of the pieces of hardware that we're working with, each qubit technology has a different set of basis gates that work well for that piece of hardware. So we need to target those instructions. We need to obey the rules of the hardware associated with qubit connectivity, operator time, any sort of particulars about the way that we program these systems in terms of the waveform generators that often need to pulse these systems. They have their own frequency and timing constraints you need to obey. And then optimization rules. So what tools do we have in our toolbox to minimize these programs in the best way? So motivating compiler research, we know what a compiler is now, so let's motivate research. We know that reliability and architectural constraints are currently blocking us from widespread adoption of quantum systems. So if we have a compiler, we're able to kind of adapt programs to those intrinsic properties of the quantum machine. And then if we think about systematic improvements through hardware alone, those aren't going to give us they're not going to accelerate us into utility scale quantum as fast as we want to go. So while we've been making hardware improvements that are non-trivial, we could be doing more in terms of like trying to maximize these systems' potential with software. So there's a lot of room for co-design, and this is where I do most of my research, hardware-software co-design, in order to kind of accelerate the timescales that we reach useful and utility scale quantum. So now with that motivation, we know what a compiler is, we have motivation of why we want to study them, why we want to build them up. Let's consider a simplified compiler pipeline that will include kind of three main components. So first, gate decomposition. Placement and routing sometimes is considered two different things, but I'm going to lump them together as one step in this pipeline, and then low-level optimization. So first, gate decomposition. Essentially, we have these algorithms that use these very complex unitaries to implement some sort of computing task on quantum computers. But we need to take those very complex unitaries and transform them into the set of basis gate operators that are supported on a particular piece of hardware. So we'll start with, we were just introduced to the Toffoli gate. So a Toffoli gate is something that's frequently seen in reversible logic. It's seen in a lot of arithmetic circuits that you'd use. And just in general, it appears everywhere in a lot of different quantum applications. But unfortunately, many technologies cannot natively implement a Toffoli gate. So you have to decompose it. If we were going to use Qiskit, I'm sure y'all will experiment with this a little bit later. But you can use Qiskit transpile to transform this Toffoli gate, this 3-qubit interaction, into a series of single and 2-qubit gates. So if we were to decompose it into a poly x, square root of x, our z rotations and controlled x gates, we would have kind of transformation 1 with gates at 1, or if we were to transform it into the set of operators that is native to the IBM devices, which includes x, square root of x, RZ, and echoed cross-resonance gate, we would get the following representation. And that they look very similar, but we can see that there are a few more gates in that gate set number 2 as compared to gate set number 1. So this is something that you often see that results from compilation. One, we see that Toffoli gate expanded. We have a lot more gates that appear in these 2 decompositions, and we can kind of see that not only do we have the number of gates increasing, we can kind of see that these 2 implementations just, depending on like what your characteristics of your hardware are, you might have 2 representations, 2 specifications that logically mean the same thing, implement in 2 very different ways. One might have longer duration than the other, and there's a lot of things that kind of have to be considered in this gate decomposition procedure. So just as a note, in this example, we aren't really taking connectivity into consideration. We're assuming that every qubit can talk to each other, but that just kind of further complicates things in the compilation pipeline. So placement and routing. Like we just said, oftentimes all the qubits cannot talk to each other. There are some qubit technologies, such as trapped ion technologies. They have can do qubit-qubit communication with all the ions that are in the trap, but superconducting qubits are really rigid in terms of their layout on chip and how the qubits communicate with each other. So placement and routing is another very important part of the compilation pipeline, where we need to we need to place our qubits on the most robust part of our chip and then route them so we minimize the number of swap operations that are needed to make a quantum circuit agree with the back-end connectivity. So we have kind of 2 examples here. So noise-aware mapping. This is a really challenging problem because quantum circuits are we have quantum programs that have a lot of connectivity requirements. They need very low error to get meaningful results out of them. But then we have these devices that not only are very heterogeneous, they have error that tends to fluctuate over time. So that's seen here with this plot to the right. We have just traces from various calibration cycles of T2 coherence time for 3 different devices that are the same size, same architecture, but we can see that they vary a lot, not only day to day, but between the devices. So creating a very challenging problem for compilation. It's not just a one-size-fits-all solution. We have to really run compilation every single time or run a compilation pipeline every single time you want to run a circuit, so you get the highest quality results with the most accurate error information. And then, of course, taking into consideration that whenever you place swap operations, just like in that picture in the bottom, you want to try to find the shortest path to minimize adding extra gates to your circuit, which will lead to extra error. Finally, we will get to low-level optimization, and low-level optimization is really where we start seeing this transformation of gates into machine code. So this is often pulse-level specifications that we can execute on hardware. So a couple of examples here we can do with our low-level optimization. Once we have a circuit that is in the gate set that agrees with the back end, once it obeys all the connectivity rules, we can start doing clever tricks with just gate commutation, gate cancellation to try to simplify our logic as much as possible. And then once we get to that point where we are able to have the most simplified, we can't minimize our cost function anymore, whatever our cost function is for a particular circuit, we can start individually taking all those gates and transforming them into their pulse level implementation. So this would look something like this. So we have a standard QAOA circuit compilation, and in this technique, we are taking each one of those individual gates, and we are kind of doing a window kind of replacement of we have a particular operation and we put its pulse level implementation kind of directly in its place. But this is an area of research in the sense that if you are able to have a little flexibility with your abstractions, your circuit level abstractions, so you aggregate instructions, you're able to use tools like quantum optimal control to design gates that are much more compact and concise. So we can see in this example that instead of doing a gate-by-gate replacement, kind of collectively, using quantum optimal control to find a new pulse level implementation for a set of operations that create a unitary, we're able to create a much shorter circuit, which is really exciting, and we can have a lot of room for optimization, but it's really challenging to decide when you'd want to do that level of optimization. So this a very simple pipeline, but there's a lot of additional complexity that we have to consider. And this is where the research comes in, and this is where help from the wider applied mathematics community would be super, super helpful. So many of the stages of the compilation pipeline are stochastic and heuristic. There's a lot of room for improvement to minimize cost functions. Whenever all these tools were first created, people were optimizing using stat solvers, which obviously isn't scalable. So now we have all these heuristics that do a good job, but there's probably a lot of room for improvement. And whenever we're thinking about things like quantum optimal control, gate synthesis, we have numerical methods that we can apply to try to find the best solution for those parts of the synthesis, but there's probably a lot of room for improvement. And then, of course, hardware and applications might need other special considerations. So what if you have heterogeneous gate sets? What if you have a larger application that you want to run on a smaller quantum machine, or you want to run in parts of it on a classical machine? What if you want to implement error mitigation and you have to optimize where you place your error mitigation? What if you want to use mid-circuit measurement? That complicates things even further. Where do you place that mid-circuit measurement, and how do you use it effectively? So a lot of things to consider. So we'll quickly wrap up. I know I'm kind of reaching the end of my time, but I really want to highlight the future directions for the quantum stack. First and foremost, just highlighting that the future of quantum technology is modular. I think everyone has generally come to a consensus that if we want to scale these systems, we're going to have to scale two systems that are composed of many parts, potentially will have many technologies, especially in this era we really don't know what the best quantum technology is. Maybe it'll fall out of research that there's a particular platform that's better for some applications than others. A lot of these devices are accessed by the quantum cloud, so how do we kind of orchestrate that communication and make sure that people can get the resources that they need and implement all of the error mitigation that they need to in the cloud, and then of course thinking about all these things with quantum error correction. It's on the horizon. We've had these very exciting demonstrations early on of quantum memory. So once we have quantum error correction, how do we fold that into the compilation picture as well? So not only do we have to compile and optimize our circuits in terms of logical qubits, rather than coding on metal itself, we need to think about this underlying layer, this kernel of quantum error correction, and that also needs its own compilation procedure to find the right code distances, to adapt to errors. So a lot of things that can be done here. Huge opportunity for scaling in these spaces with the continued theme of hardware-software co-design. So one, we can make the most of our existing architecture with software and also guide the design of future infrastructure that's more viable for scaling and can do useful things, because at the end of the day, we want quantum hardware that does useful things so we can solve these really exciting, high-impact problems. So open-ended problems for quantum software, kind of a lot of things across the board, but characterization, benchmarking, improvements in our compilation pipelines to take quantum error mitigation and error correction into consideration, heterogeneous system interfacing, hybrid HPC, ecosystem management, and then of course just continuing to scale the software stacks. And I'll wrap up with finally, the opportunities for multidisciplinary engagement. There's much space for a lot of folks in the applied mathematics space to contribute. So optimization, first and foremost, everywhere in the quantum software stack. I'm sure there's ways that we can improve this. And even with conversations that I've had with many of y'all today, I'm very excited to kind of go back to my lab and kind of implement new ways to do discrete optimization, transforming it into continuous optimization when possible, and just, new ideas for improving optimization where we, have it just appearing everywhere in the quantum software stack. So new techniques for gate synthesis, optimal control, better ways to do numerical methods and fold those into our compilation pipelines. This one's kind of a really cool topic, but formal methods for validation and verification. Whenever we are synthesizing logic, we want to make sure that it's not only done in a efficient manner, but it's correct. So I think that's probably paramount. And there's a lot that we can do to bake in verification into the compiler pipeline. And then finally, new quantum error correcting codes. I think that's a very exciting research space where a lot of folks with like a very strong basis in theory can contribute, so that maybe there's a way that we can combine the needs of applications and the constraints of the hardware together to discover new quantum error correcting codes. So with that, thank you, and looking forward to conversations.